Good afternoon, everybody. It's time to get started. Welcome, everybody. It's a great pleasure for me today to be able to introduce Mike Kahana to you. I've known Mike for maybe 6 or 7 years or something. We were on a study section together, but I've known his work since quite a bit before then. I actually came to know his work when he started doing some interesting collaborative work with Bob Sekuler, who's a vision scientist, sort of taking psychophysical methods from vision science and applying them to memory. And I liked it so much I stole the idea and started doing it myself. Mike has had a great career studying all kinds of things related to memory and related issues. Mike got his PhD in 1993 from the University of Toronto, then did a postdoc at Harvard. Were you like Bill Estys' last postdoc?
Yes.
Of course, he's like still around and kicking, right? Isn't he?
He's in a nursing home.
Oh, man.
Just recently, but he was. Yeah, he is around and kicking.
Yes. Anyway, should be kicking me. Anyway, so Mike joined the faculty at Brandeis in 1994, worked his way up the system there, and then took a position as a professor in the Department of Psychology at University of Pennsylvania in 2004. He has had lots of grant support, published many, many fine papers, recently became a fellow of the Society of Experimental Psychologists. Many of you have never heard of that. That's how elite it is. He has been on many review panels, has been associate editor at a couple of journals, and has generally done an amazing amount of really fine work over the years. So I'm pleased to introduce him to you. His talk is entitled Context and Episodic Memory.
Thank you, Steve, for the very kind introduction. It's a pleasure to be here. I've been wanting to get over here for several years, but one thing or another, medical issues had come up that delayed my trip, but it's wonderful to finally make it out and see all of you. Today I'm going to share with you some of our work on episodic memory. Episodic memory is one of the most remarkable feats of our memory system, and it allows us to do a kind of mental time travel whereby we can go back to the past and relive some experience that we have previously had. And my interest for many years has been in understanding the process of episodic memory encoding and retrieval, and in particular the role of context in episodic memory. And I'll tell you later what I mean by that. But let me start with telling you a little bit about the time traveler. The time traveler is the protagonist in a book by H.G. Wells, Time Machine. And the time traveler was sitting with his colleagues at a dinner table and telling them about his new invention of the time machine. And his colleagues, this is the late 19th century, profess a great skepticism of the possibility that you could travel in time. The psychologist says, but the great difficulty is this: you can move about in all directions of space, but you cannot move about in time. And the time traveler responds, that is the germ of my great discovery. You are wrong to say that we cannot move about in time. For instance, if I'm recalling an event very vividly, I go back to the instant of its occurrence. I become absent-minded, as you say, I jump back for a moment. Of course, we have no means of going back for any length of time. And it is this kind of mental time travel that, even though it is often subtle in its form, it's something that we use every day of our lives as we seek to re-experience, to relive previous events, or in a much more prosaic sense, when we bring to bear those experiences on our current information processing, even if we don't necessarily have any conscious awareness that we're reliving those previous experiences. There are 3 questions about episodic memory and the role of context in episodic memory that I want to consider today. What is context, and how is it represented? Context, I will argue, is the core component of the episodic memory system. It's the idea that there exists a spatiotemporal context into which experiences are placed. How that operates is the core element of the episodic memory system. It functions, it serves a number of critical functions in memory search and retrieval and encoding. And what I'd like to consider is how you might understand that using computational modeling approaches as well as behavioral approaches. And finally, recently we've begun to explore the neural basis of context and episodic memory. And in particular, we've tried to look for a neural signature of spatiotemporal context itself, mainly temporal context I'll speak to you about today. Why context? The idea of context has been around forever. If we go back to the doctrine of change of Heraclitus and Plato, the idea that every experience is somehow unique, that you can never exactly reproduce any experience, was in the heart of the doctrine of change that was a fundamental idea in early philosophical writings. And the Chicago school, led by Harvey Carr in the 1920s and 30s, and his student McGew, who did a lot of influential work on human memory, emphasized the idea of context and context change as a critical component of memory processing, and in particular of the way of the reason we forget. So we all know about McGew's theory of forgetting as encompassing the idea of interference. And interference had been around in the forgetting literature since the late 19th century, in particular the work of George Elias Mueller in 1894 and 1900. But McGew's second major explanation for forgetting was not interference, but it was contextual change. And in talking about contextual change as an account of forgetting, McGew emphasized that it was not simply the environment that you're in that defines its context, that is, the external environment. McGew argues that the internal environment, and Carr made similar points, forms a very important kind of contextual representation that is ever-changing, that includes your thoughts, your feelings, your ideas, every aspect of your mental system, and that information becomes part and parcel of every memory that is formed and is part of the process of memory retrieval. This idea was unpopular among the behaviorists because context was not something that you could easily manipulate or measure. People tried change of room situations to manipulate context. The effects were very small. And context was largely abandoned except for the work of a few people in the early cognitive approaches. For instance, Bill Estys in the 1950s proposed the idea that there are a ever-changing set of stimulus features that become associated with items that you experience. He used this to explain both animal learning and human learning effects, and that this ever-changing background of stimulation could be used to explain a number of important phenomena, such as the distributed practice effect, the finding that when you are training an animal or a human to learn some information, if you distribute the information that's being learned in time rather than blocking it together, people and animals are faster at learning. A number of other phenomena that we won't go into. The basic idea of Estys model can be described using more modern notation as a simple AR1 or autoregressive process. This is a random walk model that he proposed. Ti is the context after the ith occurrence of an item. Ti minus 1 is the context after the prior I minus 1th occurrence of an item. And the current context is the previous context plus some perturbation, some shock, some innovation, epsilon. Epsilon is just a random perturbation of the system. And in this representation, t is a vector, epsilon is also a vector, and all this equation says is that your current context is a sum of all your previous shocks that the system has experienced, so that each step of this process you make a small move in some random direction, and this context state t becomes part of your memory. Bauer extended this idea in the late 1960s to account for a number of phenomena in recognition memory. And just to illustrate the notion of contextual change as a random walk, here is a map of an old map of Philadelphia, and you start over here. If you took a random walk, after a while you might end up over here. If you take a different random walk, you might end up there. Another one, this one's going to take you back around. And what these three paths, these three random paths illustrate is a fundamental feature of random walk processes, which is that over time they tend to move farther and farther from your point of origin. So random walks have the property that the variance increases with time, and so in this case, if you know where you ended up and you know where a memory was stored in a spatial map, let's say, you can get some traction on how far back that event was encoded. The further back it would be in space, the further back it would tend to be in time. Now that doesn't work exactly in two-dimensional space, but in 1,000 dimensional space or 1 billion dimensional space, it works extremely well, which is to say the more dimensions you have in your stochastic process, the more likely it is that any given move is going to take you farther away from your point of origin. And in the limit, as the number of dimensions approaches infinity, the probability is going to be 1 that your step that you take is going to take you farther away from your starting point. And that is where we come back to Heraclitus and the notion of change, which is to say you can never actually come back to your starting point. You can never completely relive a past context because context is ever marching forward. There are many, many, many dimensions of experience, and as a consequence, your experience will constantly have a forward arrow in time. That is, it's always going to get further and further away from its point of origin. Random context models had a checkered history. They went in and out of phase between the 1960s and the 1980s. But the core ideas of those models were that context is associated with items. Context is that t vector that I just showed you. When you queue with context, it activates recent items. Why is that? It's because context is constantly moving farther from your starting point. So that means that the most recent memories that you've experienced are going to be closer to you. And the more distant memories from the past, are going to be farther from you. So here we come back to McGugh's idea that context change is a factor in forgetting, because as time goes by, as events occur, your context is going to be further and further away from the earlier experiences. So the further back in time an experience occurred, the more stuff will have happened, and as a consequence, context will have moved, and your context representation will become a less and less effective cue for those earlier memories. But if an item retrieves its context, then you can do more with it. So if an item retrieves its context, well, let's talk about one thing you can do is you could model recognition or judgments of recency. That is to say, you could retrieve the context of some item that occurred a while ago, and you could compare that context to your current context, and the difference between those two contexts tells you how far in the past the item occurred. But where you can go with that in an even more interesting direction is you can retrieve that past context, and as a consequence of retrieving that past context, you can relive or reactivate memories that occurred at that time. This is a point that Randy Gallistel made in another setting. I've made this point as well. If you imagine context moving in this direction, so if memories are like manna from the heavens falling down on me, and I'm collecting my memories as I walk in this direction, and now I get to this point and I'm here. If I look back, the memories that are most recent are the ones whose context will be most similar to my current context. But if through some path of retrieval cues I manage to jump to the memory that was encoded here, now what I'm going to remember are the things that occurred in this context, the things that occurred close to where I am now. So the process of contextual retrieval can actually be used to mediate associations. The way we've been studying this is using the FreeRecall paradigm. FreeRecall is a very simple memory experiment. In some ways, it's the simplest of memory experiments. And it allows us to study the process of memory search. Kirkpatrick in 1894 was the first to ask people to remember items in any order. In a FreeRecall experiment, you get a list of items, and then you try to recall them in any order you like. So let's do a little example of a FreeRecall experiment. You're going to get a sequence of words presented to you. And at the end of the sequence, you could imagine what it would be like to be in an experiment trying to remember this list of words. Okay. So I'm not going to ask you to recall the words out loud, but you could just reflect on what you're doing when you try to recall those words. I'm going to show you some data to describe what actually happens in a FreeRecall experiment behaviorally. What do people do? This is the classic, on the right is a classic serial position curve averaged over a bunch of experiments that we've done in my lab. And it shows you the classic pattern of recency, that is memory, the probability of remembering items from the end of the list is higher than the probability of remembering items from the middle of the list. Probability of remembering the first few items is also higher than the items in the middle of the list. That's called the primacy effect. That's the recency effect. And the gap here is because I'm averaging data across experiments that used different lengths of lists, but the individual experiments show the same basic pattern. The recency effect can be studied more precisely if you plot what's called a conditional probability serial position curve. A conditional serial position curve looks at the very first item you recall. That's this solid line with the filled circles. The very first item you recall has a very strong tendency to be the last item in the list. There's still a small primacy effect. It's not very great. There's a huge recency effect. The third, second, third, fourth, fifth, seventh items you recall, so we can see that as you go through the recall sequence, your probability of recalling the end of list items goes down. So there's a very strong tendency that people have to initiate recall at the end of the list, and this tendency diminishes as you go through the retrieval process. And these conditional curves are adjusted at each moment for the available items that could have been recalled on the assumption that people very, very rarely repeat themselves. So we assume that if they've already recalled an item, that's an item that they will not recall again. What else can we say about the way people recall lists of items? Well, the recency effect can be observed not only in the way in which they correctly recall items, but also in the errors they make. So if we plot the probability of a person incorrectly recalling an item that was not on the list as a function of how many lists back that item had appeared on, what you get is this curve. If the incorrect prior list intrusion was an item from one list back, it has a much higher probability of being produced than if it was from 2, 3, 4, or 5 lists back. Or more precisely, when you make errors and you recall items from prior lists, they disproportionately tend to come from recent prior lists, even when you've adjusted for the opportunities to make recalls from those prior lists. So recency not only is observed on the short time scale of the last 7 plus or minus 2 items that people traditionally think of as resulting from short-term memory retrieval, recency is also observed on a much longer time scale of lists. Okay, that's recency and primacy. In some ways, the most striking feature of the way in which people recall items can be observed not by plotting the probability of recalling an item from a given list position, but rather by looking at the conditional probability of making a response given the nature of the prior response that you made. So if I recalled the word house in the list, what's the probability that the very next item I recall is going to be an item that was similar to house? And in using the word similarity here, I'm going to focus on temporal similarity, that is similar in the time at which it was studied. And these are curves that plot the probability, the conditional probability of a response as a function of how far away an item was from the just recalled item. So a value of 1 means that you made a transition to the item that followed the just recalled item, immediately followed the just recalled item. -1 means you made a move 1 back in the list, 1 forward, 1 back, 2 forward, 2 back, 3 forward, 3 back, etc. And this curve illustrates Aristotle's law of contiguity. Two items that were experienced together in time tend to be recalled together. This is data averaged over many experiments. Every experiment shows the same canonical form. We've done this many times, analyzed many other people's data sets. You see several features of these curves are worth noting. First, the asymmetry. So when you make transitions, you tend to make them in the forward direction more so than in the backward direction. The contiguity effect, the tendency to make transitions to nearby items, and this plateau that at a certain point, your transitions tend to be equally probable as you keep going out further. That is, it doesn't just fall down to 0, it falls down to some asymptotic value. The same relation that you see here for the probability of making a transition, you see here for the latency of making a transition. So given that you're going to recall two items successively, if they were studied at proximate list positions, you'll make that transition much more quickly than if they were studied in remote positions, and that shows the same forward asymmetry. The forward transitions are faster than the backward transitions. This is a very important analysis for what I'm going to say down the road in the talk. So if anybody has any questions about how these data are produced, let me know, or else we'll go on. Okay. I should just point out that to calculate these functions, you don't just plot the proportion of responses as a function of lag. You have to look transition by transition. So you need to have, for all of the analyses that I do, you're writing a computer program that will look at all the possible transitions that could be made at each point in the recall sequence and asking, given the possible transitions, what's the probability that you made a certain transition? And it's very important that you do that adjustment because there are all kinds of artifactual reasons that you might expect to see different patterns in the data. So you have to adjust. You have to do a true conditional probability analysis in these studies. Oh, we measure the contiguity effect in a single number, which we call the temporal factor, and that single number expresses the tendency for participants in an experiment to cluster items in recall that were studied at proximate list positions. And if we plot the temporal factor, if we plot recall probability as a function of temporal factor, what we see is that participants who tend to cluster more show a stronger contiguity effect recall more items than participants who show a weaker contiguity effect. And in another study, we showed that older participants, all else equal, will tend to show both lower recall and less temporal clustering than younger participants. And this is both true for the young-old and the old-old groups. The contiguity effect is not only seen in the way people recall items correctly, it's also seen in the errors people make. So you could do an analysis of intrusion errors, and when people make two prior list intrusions successively, so they incorrectly recall two items that were not on the study list successively, the probability is highest that those two items will have been in neighboring positions on some prior list, and the probability is highest that those items will be from the same prior list. So the fundamental point illustrated in the error analysis is the same principles that govern correct responses govern recall errors. There's not a separate calculus that the brain uses for false memory and for correct memory. The same machinery that serves us so well in correctly remembering things leads us astray when we make incorrect responses. Yes?
Just real quick, is temporal clustering typically seen on, like, a list by list basis, or is something like you might get one temporal cluster and it's after, out of every 3 or 4 lists, or, you know what I mean? Because like with semantic clustering, it tends to be a pretty robust phenomenon.
Extremely robust, more robust than semantic clustering. Temporal clustering is far more robust than semantic clustering, unless, semantic clustering, well, I'll talk about semantic clustering, but temporal clustering is recency and temporal clustering are the two principal things that you see in recall of random word lists. Semantic clustering you see in recall of semantically organized word lists, but you also see it in recall of random word lists. And here's some remarkable data on semantic clustering, remarkable not because it would have surprised Aristotle, but because of how regular the data are. Here is the same conditional probability analysis done, but instead of temporal similarity, which I plotted for both positive and negative lags, here I'm going to put semantic relatedness on the x-axis. And we've done this several ways. This is using latent semantic analysis to determine similarity. We've done it using word association spaces, various measures that computational linguists have used to describe the similarity of two items can be used here to just simply get a metric for how similar two items are in some semantic space. And what you see is that the probability of making a transition rises sharply as the similarity goes up, where one would be, I'd say 0.6 or so, would be items from the same semantic category. But these items down here, below 0.4, these are items which if you came up with some rule for rejecting items that showed any significant semantic connections, they belong to any common categories, these would all be considered random. You wouldn't notice any obvious associative connections, and yet there is a significant increase here. And similarly, the latency data show again the mirror image. More related items are recalled more quickly than less related items. And the same pattern can be seen in the way people make errors. So if you recall an item from the list, let's say you recalled the word fountain. Let's say the word fountain was on the list, and you recall the word fountain. If you're going to make an error after recalling the word fountain, that error is more likely, at each output position in the recall sequence, that error is more likely to be similar to is going to be more similar to the item than if it were a correct response. That is to say, errors can be predicted based on their similarity to the item you just recalled. So people make errors and correct responses according to 3 laws: recency, contiguity, and similarity. I didn't mention primacy. I didn't put primacy up on this on my 3 laws chart, and that is because primacy is a much more fragile phenomena in FreeRecall. It's a smaller phenomena. It's a more fragile phenomena. It's associated with over-rehearsal and strategies. If people are strategically rehearsing items, they will tend to use the recall process as an opportunity for them to call back into memory items from the beginning of the list. Since the items in the beginning of the list have the most opportunities for rehearsal, because at each point, those items, if you have an opportunity to rehearse each item after each presentation, each prior item after each presentation, the early list items get the most chances of being rehearsed. Those items will tend to move, because they get rehearsed more, they'll tend to move later in the list. And so to a large degree, you can account for the primacy effect based on the dynamics of rehearsal. And so I'm not going to talk much about primacy today, but if you guys want in the questions, we can return to primacy. For the last 12 or so years, I've been trying to understand how you can model the data I just described. And by model, what I mean is I'd like to have a computational framework in which I can understand what gives rise to these phenomena. Otherwise, we could tell each other stories. And I like to tell stories. It's nice to tell stories. My mother was a great raconteur, is a great raconteur, and always liked to tell stories about things. But in science, stories are very slippery things, and if you get into the business of telling stories, you'll convince yourself of things that might not be true. Computational approaches force a certain kind of rigor on your thinking that makes you specify exactly what assumptions you're making, what the consequences of those assumptions are, and often you're surprised. You're surprised by the things that you cannot explain, and you're surprised by the things that you can explain. And so I've taken an approach together with my students over the years of coming up with, trying to come up with models building on the original ideas that Estys and Bauer came up with all those years ago to explain the detailed behavioral data on things like recency, contiguity, and similarity effects in FreeRecall. And FreeRecall is a challenging task to model because in modeling FreeRecall, you need to come to terms with the search process. You need to explain not only how memorable a given item is, but how does the mind get you from item to item in the retrieval process. And the approach that we've taken, which we now call the context maintenance and retrieval model. Previously, we called this the temporal context model, but Sean Pollan, who is at Vanderbilt University, just joined the faculty at Vanderbilt last year, convinced me that this is a better title for the model because it's not just a model of temporal context. It's a model of semantic context, source context, potentially spatial context. And in our recent work, we've been expanding it beyond the focus on temporal context as the exclusive source of contextual information. Sean and I proposed a hypothetical neural architecture that the model is a mathematical model, and I'll show you the equations, but here is the way we're thinking about it in terms of the brain. The fundamental idea is that you can divide information into context representations and item representations. Context representations being represented primarily in frontal areas, item representations primarily in temporal areas, though I think there's a lot of distributed representation of all of this type of information. The hippocampus being particularly important in linking context and items and context. And the core idea here is that context and items are bidirectionally associated through the hippocampal system, that items are used to drive changes in context, both directly and through retrieval of previous contextual states. And context is used to activate items, both directly, that's going to give you the recency effect, and mediated through retrieved context, which gives you mental time travel and the contiguity effect, and semantic associations as well, because of past, not only the current list context, but all the history of prior contexts, which carry semantic information in the model. I think the best way to describe the model, and for this I'll turn the lights on. I could flash things on the picture. I've tried to use cartoons for this, but I think the best way to describe it is to actually just write down how it works. It's a very simple model. I'm going to strip, in my presentation here, I'm going to strip some of the bells and whistles off the model because I want to just convey the essential ideas of the model. So in essence, the model assumes that there are two representations here, which you can think of as two representational spaces. We can call this the context space. This is the item space or content, item or content. And each of these blobs contains features. The features can be thought of as populations, as groups of neurons with differing levels of activation. Some are more strongly activated, some are more weakly activated. The collection of features here can be described mathematically as a vector. So we'll call this vector C. We can call this vector F. Historically, we've called that F. And the nature of the memory process is associating the C's and the F's together. And that's done by way of a simple Hebbian kind of associative matrix. So you can write down a matrix W, which is equal to CF transpose. You can write down another matrix. This is going to be the FC matrix. This is going to be the CF matrix, which is going to be FC transpose. And this little bit of linear algebra is just a way of saying that I'm going to form an outer product matrix whose elements are the products of the activations of each pair of elements in these constituent vectors. So if this guy is connected if all of these guys are connected to all of these guys, if all of these guys are connected to all of these guys and vice versa, then the strength of a connection is related to the correlation between the two activations. That's the basic Hebbian principle, and that's captured in these outer product matrices. But the core equation for this model is the equation that describes the evolution of context. And for that equation, what we would say is Ct equals rho Ct minus 1 plus a scale factor beta times WCF, sorry, WF, where is this? Yes, that's right. F sub t, mix up these notations. And this equation is a little more complicated. What this equation says in English is that the context at time t is a weighted sum of the previous context plus something that is driven by the new input to the memory system. And that new input is f sub t. That's the experience at time t. So to put it another way, where your current context sits is a little bit of your previous context, actually a lot of your previous context, plus a little bit of a new contextual element that is driven by your experience itself. And the reason that we have this matrix W here is that we assume that what it is that you add to your context representation is not only driven by your current experience, but it's driven by all the thoughts and ideas and feelings and emotions and associations that that experience conjures up in memory. So that's what the W is going to do. It's going to allow the item to pull out all of its previous associations in memory, including both semantic associations and temporal associations, and use those to drive the contextual process. And so in a sense, in this architecture, the way it's written here, your context includes within it a weighted sum of your experience. Unlike the Estys context, which was random noise, the context in our framework is actually something about your current state of what features in your experience are active. Yes?
In your model, so exactly which time point vectors F and C are used for the WFC in the model?
So I should have written it like this. So the change in W at any given point is the product of CTFT or FTCT.
So the W gets updated at every moment, and then that is used to construct the next context, which then
Precisely. Exactly. That's right. And now, if you take W, let's say you take W FC, and you multiply it by F, what you're going to get out is a weighted sum of contexts. And if you put in WCF times C, you're going to get a sum of items. And the assumption in the model is that memory is a function of the constant interplay between items and context. So if you start with context in a free recall experiment, I give you the context. What that's going to retrieve, WCF times the context, is going to give you a recency-weighted sum of the items, which will allow you to retrieve the most recent experiences. I'll tell you how that works in a moment. And when I retrieve one of those experiences, that comes back over here. Now WFC times F is going to retrieve a combination of all the contexts associated with that item, which in turn will drive the retrieval of the next item. And so you bounce back and forth between these three equations, actually all of these equations, because as you retrieve information, you're updating the weights and you're updating context. So dynamically, you're updating weights, you're updating context, and you're guiding retrieval. And the whole dynamics of these 5 equations, these 2 being more of the retrieval equations and these 3 being the it's hard to specify specifically encoding because encoding and retrieval are going on constantly. But if you're, the dynamics of these 5 equations govern what's going on in the model. The last thing I need to tell you about the model is that we assume that there's a probabilistic choice rule that allows you to select items from memory based on the inputs that you get. And the way that probabilistic choice rule works is that we assume that the activation of each item in memory drives a diffusion process, a random walk process, toward a decision boundary. This is a standard model in choice type models. It's the work that Roger Ratcliffe and others have done. We assume that there's a race between all the competing items, and the first item to cross the decision boundary is the item that gets recalled. When an item is recalled, we assume that that item has now gets an elevated the criterion for recalling that item is temporarily elevated, which prevents you from keeping on recalling the same item again and again. So there's a decay process there. So the item that's been recalled now gets degraded in terms of its competition for subsequent recalls until a while has elapsed. And on the process goes. This allows the model to capture time in recall, which means that the model can give you not only which items are recalled, but when they're recalled. And the model does a very good job of fitting data on inter-response times. It also allows the model to determine when it's done recalling, because if the time has been used up, then the model stops. So let me just show you, we can come back to questions about the model, but let me just show you some of what the things the model can do. Here are classic data from Murdoch 1962 on serial position effects in FreeRecall for 20-item lists, 30-item lists, and 40-item lists, showing the recency effect. These data have been used to argue for short-term memory as a distinct processing system, as distinct from long-term memory. The idea is that memory for these early list items and mid-list items represents retrieval from long-term memory. The recency effect, which shows this precipitous decline for 20, 30, and 40-item lists that lie right on top of each other, if you were to align them to the right, is evidence for short-term memory. That is to say, there doesn't seem to be any proactive interference effects in these short-term memory data, but that's not quite true. The model has no short-term memory whatsoever. The model has no distinction between short-term and long-term memory, yet it has no trouble accounting for these data. It uses a kind of rehearsal type process to give you the primacy effect. That's not very interesting because in the data you need some process to give you the primacy effect. In the model you need one too. The model produces the exponentially growing inter-response times that you see in recall tasks. Here's classic data again from Murdoch and Ikeda 1970 for 4, 5, 6, and 7 items, people recalling 4 items, 5 items, 6 items, or 7 items. And the response times go up as you go through the retrieval process, forming this family of curves. And the model does the same thing. You don't need any machinery to explain this other than the dynamics of the retrieval process. That is to say, this falls out of the model quite naturally. The most important phenomena that I feel the model captures in a kind of in an innovative way is the contiguity effect. So here's the contiguity effect in the data. Here's the contiguity effect in the model. In this study, it's not a precise fit because we're fitting about 20 other features of the data at the same time. But the important point in how the model captures the contiguity effect is the model has no direct item-to-item associations. Items are not connected by way of direct associations. And this seems completely implausible or counterintuitive. It certainly seemed that way to me. The Gestalt psychologists pointed out in the 1940s, Curler, Schleim Ash in the early 1960s, Irv Rock in the late 50s, pointed out that association is the creation of a new cognitive representation that integrates items together. Well, I agree with that. That's what happens in paired associate memory experiments, where you create a new whole from 2 constituent parts. And it may be that that also happens in FreeRecall experiments. But you don't need that in order to form associations. And in fact, it's appealing that you can create associations simply by virtue of the shared temporal context in which 2 items have occurred. The model predicts the phenomena that we've all known, that if you delay testing, the recency effect that you see strongly in immediate recall is greatly diminished in delayed recall. That's just the classic idea that you knock the items out of the short-term memory, though here there's no short-term memory. So where are you knocking the items out of? What you're doing is you're perturbing context. And if you created a longer delay, you would flatten this curve out completely. So the model predicts the classic phenomena of rapid decay in short-term memory. In fact, there is no short-term memory in the model. What the model does that other models of short-term and long-term memory cannot do is explain the long-term recency phenomena and, in fact, the scale invariance of recency. So this is data from experiments like Bob Bjork did in the early 70s, where you give people a list of items, but after each and every item, you have them do a series of complicated arithmetic problems. They're not very complicated, but they have to do them very quickly, and they get penalized if they make errors. So father, they do some distractor task. Island, they do a distractor task. Picture, they do a distractor task. And then they try and recall the items in any order. And what you find is that the recency effect, which was eliminated, which was attenuated after a distractor at the end of the list, comes back when you have a distractor after every list item. The model does this because associations are mediated by context and because the gradient of associations does not have a finite temporal window. That is to say, short-term memory, it's like a buffer. In the model, there's no buffer. It's just simple decay of contextual similarity. What time do you guys go till here?
So usually 1 o'clock or so.
To 1 o'clock, okay. So I'll just quickly show you a couple more slides, and then we'll maybe wrap up. So if you do the same experiment with distractors between each item, you find that the contiguity effect is undisrupted. That is to say, distracting people between each list item does not alter the contiguity effect. It's a remarkable behavioral phenomenon, and the model captures it, and it captures it for a very simple reason. It captures it because both recency and contiguity are essentially timescale invariant, not exactly timescale invariant, and that's because both phenomena are graded and recall is a competitive process. So let me just use 5 more minutes, if that's all right, to show you new data that we've been collecting on a neural signature of contextual retrieval. This is the basic setup. Patients are neurosurgical patients with epilepsy who have implanted electrodes, and since Arne Ekstrom is here, I don't need to explain to you too much about the techniques that we use. He's probably told you about that, but here's a illustration of a grid of electrodes on the cortical surface. These are depth electrodes inside of the brain. Here are electrode locations across 67 patients that we've been studying in different views of the brain. So you get a lot of recordings from all over the brain in these patients. They spend about 2 weeks in the hospital, during which the neurologists are trying to pinpoint the location of their seizures. During that time, we have them do cognitive tasks, memory tasks, or like Arne would do, spatial navigation tasks. In this study, we're interested in looking at neural activity during free recall. And although occasionally we get microelectrode recordings and can record individual nerve cells, today I'm going to talk to you about a study that's only looking at local field potentials. So here we can take the local field potential and break it down into components at different frequencies. Delta, theta, alpha, beta, and gamma are low frequencies, 2 to 4 hertz, 4 to 8, etc., up to 140 to 100 hertz or 40 to 120 hertz. And we can describe the brain state when you study a word, let's say the word ink, or hat, or tree. We could describe that brain state as a matrix representing the power at each frequency band at each electrode. So let's call that the brain state associated with a given item. And here's what happens in a list. We study a list of words. Each has its associated brain state. The patient recalls the words in any order they like, free recall of the words. And we look at the brain states at encoding, and we look at the brain states at retrieval. And what we're trying to do is to find out if, in fact, this context-based theory is correct. It makes a very specific prediction about what the brain states should look like at retrieval in relation to encoding. Specifically, it says that if you're doing mental time travel, if when you recall the word cache, your brain is resetting partially to its state when you studied cache, then this pattern here should resemble this pattern. But if context is part of the representation that's associated with every item, and if this representation includes context, then this pattern at cache should not only match cache, but it should match cache's neighbors. So let's see if that happens. So first we take these matrices, we do principal components analysis, we select features that exhibit a fundamental property of context, namely they change slowly over time, they're autocorrelated features, and we do the critical comparison between the representation, the vector of your brain state when you recall cache, and the brain state not only when you studied cache, but when you studied the neighbors. If this was just random noise, what you would expect to see is that cache should show a little bit of similarity to this guy, a little bit less similarity to here. Similarity should fall off in a slowly graded manner as you go back in time, if this were just noise. If this were what the model predicts it would be, then the model should show a sharply graded similarity, and it should not just go backwards in time. It should be exhibiting a contiguity effect around the recall of the word cache. And that's what you see. So that's the contiguity effect in neural similarity space. And that's the contiguity effect in the behavioral data from the same patients. And the two are significantly correlated. So patients who show a stronger contiguity effect in the behavioral data show a stronger neural context reinstatement effect in the neural data. And this point being higher is just the item. In a sense, you're getting an extra boost for the items. And for those of you who are interested in where this happens in the brain, well, it's a pattern analysis, so it happens all over the brain, but we ran it for 4 different lobes. And you see that in temporal cortex and in prefrontal and in frontal cortex, you see a very strong effect. And in parietal and occipital cortex, you don't see much of an effect of this kind. So to sum up, what I've argued to you today is that context is a critical part of how the episodic memory system works, that we store item-to-context associations. What is context? It's a temporal integration of items that's weighted by recency. If I queue with current context, it's going to give me a recency effect. It's going to activate recent items more than earlier items. And if I recall an item, I'll reinstate its context, which is going to give me the contiguity effect by activating neighboring items. You see contiguity and recency at both short and long-term timescales, contrary to short-term, long-term memory theories that argue there are separate systems. Here you see the same effects at both scales, and you see it in the data and in the model because the model assumes a graded relation. Basically, forgetting is a graded function of temporal distance, and contiguity is a graded function of temporal distance. So you only need one retrieval process to get both short-term and long-term forgetting and short-term and long-term associations. I didn't talk to you about semantic stuff. We'll skip that. The last thing I'll just mention briefly is that we've simulated data from amnesia and aging as impaired item-to-context encoding and retrieval, and it does a pretty good job. And our latest evidence suggests that neural representations of context are reinstated at the time of recall of an item. So I'll thank my collaborators, Mark Howard, who developed the original version of the temporal context model with me. He's a professor at Syracuse. Per Cederberg, who's now at Ohio State, and Sean Pollan, who's now at Vanderbilt, and Lynn Lonis is working on the latest version of the model, and Jeremy Manning and Sean Pollan did the context reinstatement analysis that I told you about. So thank you very much.
We have time for some questions.
Yes?
So I was wondering, in your neural model that you had about halfway through the talk, where you mapped out where you thought this stuff was happening in the brain, you had this context specifically supported by prefrontal areas. I was wondering why you have it there, or how that might also interact with other models that suggest context being supported by more medial temporal areas, such as very example.
Right. So Sean Pollan reviewed the neuropsychological evidence and the fMRI evidence that in this paper that we published a couple years ago. And although context effects are often seen in medial temporal lobes, it seems that the kind of, when we're talking about context, we don't just mean, so context reinstatement depends on medial temporal lobes, but the idea of there being a context representation that's maintained, the maintenance of context, is in the model associated with prefrontal cortex. So it's not as if in the model, this is what we're thinking of as being associated with prefrontal cortex, but hippocampus and other medial temporal lobe structures are extremely important in both the formation and the retrieval of the associations between items and context. Andy?
So maybe following up on that a little bit, I guess I'm trying to understand how, to what extent you see this integration of item and context as like a controlled, effortful process of putting these things together. I mean, subjectively, it sort of seems like it's kind of hard work to do that at some level. I'm trying to remember link stuff in context, but the way you talk about it, I almost think, well, maybe you're thinking about it more automatically. It's just, it happens and you don't even need attention.
That's a great question. I think it certainly happens without attention, but I think that attention and effortful processing and deep encoding and all the things that we know to have a big effect on associative learning are extremely important. So you do get some associative effects even without intention, even under incidental conditions, but they're very weak. And in these experiments, we work hard to get people to try and integrate items into their context, but to some extent, it's going to happen automatically. Now there's going to be, context is going to move along, and so in a sense, you can get context change, I think, this process without much effort. I think it's this stuff that's going to take more effort. It's the associating the items to their context that's going to take more effort. And a healthy medial temporal lobe system.
I'm wondering if there are environments that you can speed up different components. I mean, you start talking faster, does my context change more quickly?
Yeah, I think if there's a greater rate of information, a greater rate at which novel information occurs, then context should change more quickly. And we've actually done some experiments where we vary the rate of presentation of items, and you see you can manipulate the contiguity effect. You can actually bias it. So normally, let's see which way you're looking at it. Normally it looks like this, and if you either slow down or speed up the presentation in systematic ways, you can get it to look like this. You can get it to look like this. You can actually bias it because the different components are going to be affected by the rate of temporal change in context in the two directions. Yes?
I'd like to ask a question that I think is related, but I'm not sure. So one of the things that I think is really interesting about this is that you're looking at how context controls memory search. It seems very similar to the way that people are thinking about context controlling visual search through the perceptual environment. But there it's very obvious what the role of attention is, because you have eyes and they point at one spot at a time. And another thing that happens in visual search is that things are very selective. That is, relevant sources of information control search, and you can ignore irrelevant dimensions. So I'm wondering, in your context representations, what gets stored in the context? Is it just relevant information, or is it everything, or is that controlled by attention? So in your FreeRecall experiments, you're looking at the recall of the relevant information. But there's all kinds of other stuff going on, and when you're showing the intracranial EEG data, of course there's a lot of other stuff going on in the brain that's not relevant to the words that they're looking at.
Right.
So what do you think the role of relevance is?
Well, I think that it has to be the case that attention is controlling, is gating what features are entering context, and if you have a person who is doing what we want them to do in the task, then their context is going to be largely driven by the items. And if they're daydreaming about something else, their context is going to be driven by whatever they're daydreaming about. And I thought it was amazing that we found that effect in the neural data. And we've done every kind of test to rule out confounds, and it's a very real effect. And we have a lot of data. So it's to tease out that effect in the data required. I mean, these are data from about 5,000 or 4,000 electrodes in 67 patients with implanted electrodes. So, this is, it's not clear what the baseline would be, like how, and the other thing, of course, here is that we're selecting features that exhibit this, we're doing this feature selection that we're looking for features that exhibit this property of context. But absolutely, there's a lot of other stuff going on in the brain, but it's going to average out in the wash with that much data, and that was the hope. We've tried to replicate this recently with scalp data. We have a lot of scalp data, and that's one of the things we're trying to do. And the effects in the scalp data are very weak. We only found we had 7 or 6 large data sets, and only one of them showed a trend in this direction. The others did not show any trends in this direction. So, Sharon?
So I'm wondering if you know, with the Jeremy Manning data, if you analyzed it slightly differently, or maybe I didn't understand exactly the analysis, but if you were to say, let's take a word like ball, and just, or not just ball, but like any of the recalled words, and you just calculated the, you know, the temporal correlation function with the surrounding ones versus non-recalled words, and you calculated that temporal correlation function.
At encoding, you mean?
At encoding.
At encoding, okay.
Would you see, I mean, I guess, I don't know
Yes.
if you've done that, would you see a greater correlation for the items that are not recalled, because presumably there's more maybe more interference between those items?
Okay, I'm not 100% sure I fully understand the analysis, but if you, okay, so I don't know, we haven't done this analysis saying what is the, well, how would you do it for not recalled item? Because we're conditioning our analysis here, so we're saying we're looking at what happens during recall. So you're saying if you didn't recall the item, this is the similarity of this guy to, we're looking at the similarity of this guy to this one, to this one, to this one, and to this one. We're not comparing these to one another. If you compare these guys to one another, which is maybe the analysis you're thinking of, then what you get is you get a measure of contextual drift in the neural data. And we've done that analysis. And if you do that analysis without selecting features, you get a significant change. If you do it with selecting features, you get an even more significant change, but that's mechanically going to be enhanced because you've chosen features that exhibit that autocorrelated property. Now, has Jeremy looked at what happens if you look at items that are, if you do that analysis for pairs of items conditional on whether or not they were recalled? I'm not sure what I would expect, but yeah, I don't think he's done that analysis.
Yeah, the reason why I'm thinking this is during retrieval you get a benefit from that shared context representation. But you can imagine the more similar those contexts are during encoding. I mean, and maybe this is
Oh, I see.
They're actually kind of competing with one another.
Yes. Oh, that's a good, now I see your point. That's a really good idea. You should do that. I should tell him to, okay, that's good. I'll write that down after the talk. Yes, so you could look, in other words, you could ask whether the dynamics of context here at encoding predict which items get recalled later, rather than saying, I know I've recalled the item, and let's see whether there's evidence of context reinstatement. So that's a really good idea.
That's a simple way of saying what I was trying to say.
It's easier after I've thought about it 3 times your, okay, thanks.
One more question.
Yes?
For your retrieval data, have you tried with TMS on over the prefrontal cortex in order to test, the role of context in that, anatomical structure?
No, it's a good idea. I don't have experience with TMS, but certainly if you can manipulate the context, if the context vector is prefrontal and you can manipulate it with TMS or some other manipulation, then you could have some interesting behavioral sequelae. Maybe you should do that. Yeah, you should do. That's a good project for somebody to do. I'm not going to do that, so. Okay. All right, great. Thank you very much.